We're going to continue on here with chapter 12, which is kinetics. And last time we were talking about, and we went through several examples of how to properly sort of figure out the orders of the reactants so that you can complete really the rate law and also figure out what the value of the rate constant is. Again, in most situations, when you are trying to figure out your orders for your rate law, we would have our rate, for example, a to the x and obviously b to the y here. It is very common that we will have really a table given to us of concentrations and initial rates. So you'll have a table where you'll have the concentrations of your reactants. You'll also have the rates given to you. And it may be, as we saw in some cases, a few entries, maybe more, 4 or 5, or a bunch of different entries. But ultimately, the best way to sort of approach it is sort of a mathematical approach where we could kind of take, as we did, rate 2 over rate 1 equals our k, a to the x, and b to the y. And as we did last time, the goal here is to obviously make the calculation a lot easier for yourself. So we do want to limit really the number of unknowns that we have. So when we go to the table, once again, we're not going to choose just the first and second entry maybe, but we are looking for 2 entries from the table where, one of the concentrations basically stays the same and the other sort of varies. And as we also talked about last time, a lot of times if you maybe pick the one that has a larger rate and kind of put those numbers up on top, it will kind of give you a little bit nicer whole numbers in a lot of cases. Once again, you don't have to necessarily do that, but it does make it a lot of times a little bit easier. If you do get to a situation where you look at it, maybe you can't just figure out what the exponent would be at the end. We did a couple where, they kind of worked out really nice, like, 2 to the x. In this case, obviously, x would equal 2. If you're not really sure, one way you could solve it, again, is just to take the natural log of both sides. And when you take the natural log of both sides, that does drop the x down. And then you could just divide the natural log back to the other side, gives you 2 and x. If the numbers really don't come out super perfect, which sometimes they don't because they are experimental values, obviously, in most cases, it is fairly safe to round to the nearest whole number if it's obviously some numbers, pretty close to a whole number. So I think maybe we had something like a 3 and like maybe or 3.99 or something like that, which is obviously 4. We also saw that you could potentially choose more than one set of entries for a particular reactant. Like I think I did in that one example, all 3 possibilities for that one. And ultimately what we saw was pretty much it was 2, right? We had like a 1.98, we had like a 2, a 203, so again, you can in most cases do a little bit of rounding on these, especially on ones where maybe it won't pull in perfectly a whole number. Any questions on any of that stuff there? The other thing that we did obviously was once we've got the orders for all the reactants, that would obviously give us our completed rate law that we then could go back and use that completed rate law and actually solve for the value of the rate constant. Once again, when you do go to solve for the value of the rate constant, it really could be any entry you want in the table. They all should really come out the same. And that is because that's really sort of the constant value that we could get for that particular reaction. So again, you could go through any of the entries and use those values. Just can't mix and match, obviously. So I think where we sort of left off was this very last example here that we started working on at the very end, and perhaps you finished or didn't, but let's just take a look at it here to finish out this conversation. If we start with the sort of generic rate law here, this would be our NH4 plus to the X and our NO2 minus to the Y in this particular case. Once again, in analyzing this table, we got a number of different entries. So I'm going to do our normal thing here. I'm going to look for somewhere where we keep the concentration of one of the reactants constant, which, just quickly looking at it, 1 and 2 here is going to keep that guy constant and obviously vary the other. So that's what I'm going to use to calculate my first one. So I'm going to use experiments 1 and 2. And in this particular case, I'm going to put number 2 up on top since it has a larger value for the rate. And that would be 32.3 times 10 to the minus 7. So you want to make sure you do look at the table and not miss important information that's in there. In this case, it wouldn't really screw you up too much until you got to the rate constant. Then it would mess you up. But here you'd still be okay if you missed that. This would be K and then 0.06 to the X and 0.2 to the Y. So once again, this is all the information from number 2. We're going to put our number 1 in there. So that's going to give us 10 to the 8 times 10 to the minus 7. Our K, 0.02 to the X and 0.2 to the Y. So once again, here we're going to do a little bit of calculation and see what we end up with. So on the dividing here, really, this is a 2.99, I believe, in this case. Pretty much the 3, I think. This will again cancel out. This guy here will give us a 3 to the X, and these guys once again will completely cancel out. So again, in this case, I'm just going to round. You could do the natural log, but you'll end up probably about the same answer here. And we're going to go with X is equal to 1 in this case. Any questions on that there? Going now to vary our other concentration and keep the NH4 plus constant. It looks like we could do that by taking experiments 3 and 4. We'll basically do that. So if we take experiments 3 and 4, I'm going to put experiment 4 up on top. So once again, I'm going to make sure I don't forget the times 10 to the minus 7 in this case. That's going to give me our 0.2 to the X, 0.0404 to the Y. Putting my 3 on the bottom, 10.8 times 10 to the minus 7, K 0.2 and 0.0202 here to the Y. Once again, doing a little division action here. Going to give us a 2 on this side. Once again, these are going to cancel. These obviously will completely cancel. And that looks like that should probably be a 2 as well. That's going to give us a Y is equal to 1 in this case. Any questions on any of those steps so far? Now that we have the orders here found experimentally, we know that the overall order here is going to be 2. 1 plus 1 is second order. We could write our completed rate law. And that would be the rate is equal to K times NH4 plus times NO2 minus. Once again, here we're going to rearrange this and solve for K. And K in this case would be the rate divided by those concentrations. Once again, here you could choose any of the entries in this table. And this is really where you would be kind of screwed up at this point if you missed the times 10 to the minus 7. Again, the other ones would have worked out perfectly fine because they're both times 10 to the minus 7. But here you want to make sure, obviously, that you hopefully didn't miss it. I'm just going to take the first entry. So this would be times 10 to the minus 7 divided by our 0.02. And our 0.2 molar in this case. This is going to get us a Looks like we'll go with 2.7 times 10. 2, 3, 4 to the -4. Maybe 2.70 times 10 to the -4. Now our units here will end up being molarity on top and one of them on the bottom will cancel. So much like we saw a couple of times before here, second order, 1/molar seconds would be our units that we see here for our rate constant. Any questions on any of those steps there? Okay. So clearly you need to be able to do this and calculate all those things, the actual orders for each of the reactants, the value of the rate constant, and figuring out the overall order for a particular reaction. Any questions on any of that there? All right, so the next thing we're going to talk about is actually specific orders of reactions overall. And there's really sort of 3 common orders of reactions overall. And most of the time we deal with first orders, 0 orders, or second order reactions. As I mentioned before, if you just think about, again, a majority of sort of the reactions that maybe you've come across, for the most cases, we either have kind of 1 reactant, we have 2 reactants, maybe 3 reactants, but you don't really start seeing reactions that have a lot more than that happening. So, there is almost a very common set of orders that occur in first order, 0 order, and second order reactions are again very common sort of orders of reactions that do occur really because of the number of reactants that we start with. So it's very uncommon that something would be, say, 4th order, and you would have like 1 reactant that gets you like a 4th order reaction or something like that. So the first one is a first order reaction here, and there's really kind of 2 ways you could get there. You could have a single reactant, which is obviously first order. You could actually have 2 reactants where one is maybe 0 order, right, which would give you 1 and would give you nothing, and one that is first order. So again, there's a couple different ways you can get there. If we write the rate law for a first order reaction, looks something like this. And if we solve for the rate constant here, we get the typical units that are associated with a first order reaction. So I think I mentioned it last time, and it's very common in sort of kinetics problems that they really will not tell you, hey, this is like a first order reaction or a second order reaction. But what they will do is give you the actual values or the value of the rate constant. And based on the units that you see there, you should be able to figure out, oh, we're dealing now with a first order reaction. So typically for first order, it's reciprocal seconds, 1/seconds. But does it always have to be seconds? The answer is no. It's actually 1 over a unit of time. Could be minutes, could be hours, could be days, could be weeks, could be years. But some type of 1 over a unit of time is very indicative of a first order reaction. Why do we roll with seconds? Because frankly, when we do experiments, most of the time, that's kind of what we kind of record. We do them in seconds. We don't typically do experiments over years or weeks or months. Sometimes we do, but not in very commonly. So very commonly what we record is, how many seconds this reaction ran for and those type of things. So that's again, why is the common sort of unit that we see. Now, when we look at a first order, there's really 2 types of graphs that we see. The first one is the one on the left there, which is the concentration versus time. And as we would expect in a first order reaction, as this reaction takes place, basically the concentration of our reactant is decreasing with time. So we see that kind of curved graph that's occurring. In most cases, when we are dealing with specific orders of reactions, we really like to look at things in sort of a linear fashion. And that usually brings up the straight line, which is y is equal to mx plus b. So a lot of times when we're dealing with kinetics, we like to look at those linear relationships that occur. So if we kind of take the natural log through this first order reaction equation here, we get what is sometimes referred to as the integrated rate law, or the concentration and time version of the rate law. And that is for a first order equation, specifically this one here. This is the natural log of A, which is like your final concentration, is equal to the natural log of A naught, which is like your initial concentration. K is your rate constant. And T here is time. So not temperature, it's actually time here in this particular case. And when we take that integrated rate law and we basically rearrange it and write it in this fashion, that the natural log of A is equal to minus KT plus the natural log of A naught. This is the first order equation written in the form of a straight line. This is y would be equal to mx plus b. This is important because this tells us pretty much what the graph for a first order should look like in a linear relationship. On the y, you should plot the natural log of A, which is what we see here. On the x, you should plot time, which is what we see here. And if you do so, and this reaction is a first order reaction, you should end up with a linear relationship, as we see here in this graph, where the slope of that line will equal negative of the rate constant. So the slope here will equal negative of the rate constant. First off, any questions on that there? Now, speaking of that, when I look at this line here, does this line have a positive slope or a negative slope? It does have a negative slope, and that is why the slope here is equal to negative of the slope. I'm sorry, the rate constant is equal to negative of the slope. The negative value for the slope times the negative that's in the little negative m turns our rate constant into a positive number. So again, here you should yield a positive number for your rate constant, and that's how that works. You should end up with a negative slope if you did it like in Excel, got the line, and that negative times the negative there will turn your rate constant into a positive number, which it should usually be. Any questions on that there? So another important relationship here, which we'll see in a slide or two, but I'm going to write it here as well, is what is referred to as the half-life. And the half-life of a first order reaction is equal to the natural log of 2 divided by the rate constant. And you sometimes will see it written 0.693 over K. And that is what you get when you take the natural log of 2 on your calculator, by the way. The half-life is pretty much what the name implies. It is the time it takes for half whatever you got to go away, right? So after like 10 half-lives, it's probably gone at that point. We will see this also a little bit later on in another chapter. All radioactive decay follows first order kinetics. So all of it follows basically these type of guys here. So a few things that's really important for first order kinetics here is you definitely should know the units that we see associated with K. You should know the integrated rate law here. You should know the half-life. And you should really know this equation and really this equation. It does show up occasionally, or not equation, but really graphs, basically. But those graphs are first order graphs. Any questions on that there? So again, if you got a problem where it does say it's first order and you want to figure out, you know, how much concentration is left after 40 minutes, then you would use this equation to do that. And once again, they may not tell you straight up it's first order, but if you see those units, it should help you understand that. So why don't we try one here? Reaction is 2A to B. is first order in A with a rate constant of 2.8 times 10 to the minus 2 reciprocal seconds, how long will it take for A to decrease from 0.88 to 0.14 molar? So take a couple minutes to see what you come up with. Okay, let's take a look. So it definitely tells us in this particular case that it is first order. Once again, if it didn't tell us it's first order, we would definitely know that because it does give us the rate constant here. The units that we see associated with it is reciprocal seconds. So that automatically sends you to that first order sort of equations that we talked about. Since obviously we have some concentrations, we're looking for time. That definitely is our first order here, which would be the natural log of A equals the natural log of A naught minus KT. Here, the rate constant is 2.8 times 10 to the minus 2 reciprocal seconds. Our initial concentration here is going to be 0.88 molar. Our final concentration here is going to be 0.14 molar. So we're going to pop those in there. That's going to give us the natural log of 0.14 equals the natural log of 0.88 minus 2.8 times 10 to the minus 2 reciprocal seconds times time. So we want to solve this mathematically correctly. So mathematically speaking, I personally would do this. I'm going to take the natural log of 0.14. Then I'm going to subtract the natural log of 0.88 to the other side. And if I do that, that will yield me something like minus 1.838279485. I didn't feel like rounding anywhere there, obviously. Equals negative 2.8 times 10 to the minus 2 reciprocal seconds times time. I then need to divide that to the other side. Yes. So we're then going to divide 2.8 to the negative 2. That's going to give us about a time that will be, and we'll call it 66 seconds. Units of seconds here when we divide becomes seconds. By the way, the molarity here, technically speaking, becomes a fraction. The molarities cancel out when we subtract those two. So that's where the molarity disappears too. Any questions on that? So pretty quick, we could drop the concentration here from 0.88 to 0.14 in about a minute. It will drop all the way down to basically that concentration. Any questions on any of that math there? Okay. So the half-life equation specifically for first order is found as the natural log of 2 over K. And once again, if you can't remember the half-life equation, but can remember the actual whole equation there, all you have to do is kind of what they did here. Take the natural log of 2 basically and substitute it in there and solve for time. And that would give you really your half-life equation in case you ever want to derive that formula. I would probably just want to remember it and not have to derive it there, but that does give you that. So what is the half-life here of N2O5 if it decomposes with a rate constant of 5.7 times 10 to the minus 4? So once again, we see the reciprocal seconds. So that again is how we know that this is really first order. And that means we definitely should use this. And our half-life here would be the natural log of 2 divided by a rate constant, 5.7 times 10 to the minus 4 reciprocal seconds. Gets us, make sure we use our exponent button for sure. Otherwise, you're going to find yourself kind of off there. That's going to give us like 1216 seconds. Looking at the only number we got rolling there has 2 significant figures. So perhaps up to about 1200 seconds or about 20 minutes, basically. So basically every 20 minutes, half of this guy decomposes. So pretty quick. and we'll kind of go away. Question on that there. Now, speaking of this equation here for the first order, it's really important to understand that a lot of times you will have to use perhaps the half-life equation with the integrated equation together, because a lot of times they may not give you the rate constant, but they may give you the half-life. And you would use the half-life equation to figure out the rate constant, and then you could go into the other equation, solve for something else, you know, whatever it may be at that point. So it's very common. You got to use both of those equations together. The other thing where people frankly screw up is in units. So when we look at this equation, it is really important. And it usually happens right on these two terms. So not always will the rate constant and the units of time be the same time unit. So you may have one that's in seconds, you may have one that's in minutes. So you got to make sure at some point along the way, before you use them together, you get them in the same unit of time. So that's also a very common mistake that a lot of people make, is not watching those sort of units of time and going into that equation there. Any questions on that there? All right, so here's obviously a graphical approach to half-life. And as I said before, we'll see it when we get to nuclear chemistry, but all really radioactive decay does follow this pattern here. And obviously we can see as we go from one half-life to the next, we're losing half of our green circles there. And again, about 10 half-lives, pretty much not too much should be left. All right, let's try another one here. The reaction of this guy's first order with a rate constant 2.9 times 10 to the minus 4. Find the concentration of SO2Cl2 at 865 seconds when we have an initial concentration of it of 0.0225. Let's take a few minutes there, see what you come up with. Okay, let's take a look, see how we're doing. So again, they were nice enough to tell us first order, but a lot of times they are not. So if we needed to, we could look at that units associated there. And again, that tells us we should be using our first order formulas here. So we have our first order formula, which again would be the natural log of A is equal to natural log of A naught minus KT. In this particular case, we're actually looking for our final concentration, which would be this side. So we are looking for natural log of A equals the natural log of our initial concentration, 0.0225, minus our rate constant, which was 2.9 times 10 to the minus 4 reciprocal seconds. And in this case, we're rolling for about 865 seconds here, which would be our time in this case. As we just talked about, we are okay in this particular example in terms of units. They're both seconds, but again, sometimes they are not the same units as you kind of go through there. Any questions on any of that there? So pretty much we could clean up everything on the left-hand side there. If we clean up everything on the left-hand side, we can take the natural log 0.0225. It equals, then we're going to subtract it from 2.9 to the negative 4 times 865. In parentheses would be a good move on that, by the way. Going to give you the natural log of A equals minus 4.0451, if you want to call it that. To get rid of the natural log on the left, I need to do what to both sides? Do a little inverse of natural log, a little E action to both sides. Yeah. When I do the E on this side, that just goes away and it just becomes the concentration. When I do it on this side, I'm going to take the whole number in my calculator. And if I do it with the whole number in my calculator at this point, looks like we yield something like 0.0175, and it would be molar as it is a concentration in this particular case. Any questions on that there? By the way, I do this and I could sort of make sure it makes sense. It makes sense why in this case? Makes sense in this case because my final concentration should be more or less than what I started with. Should be less, right? Because it's basically decreasing over time. So obviously here, if I hit a number at the end there, that's more than what I started with, you're going in the wrong direction. Yeah, so your reaction is going the wrong way. Any questions on any of that move there? Now, obviously, you did a little bit of rounding there on that 4 point something number. You'll get a slightly different number for sure. So again, personally, I would not round maybe to the end and then do it. But you definitely, when we start using things like the E function there and things of that nature, just slight rounding difference will give you, you know, a little bit of a different answer for sure when you use those numbers. Other questions? Was that your question? Yeah. Okay. Other questions? Okay. All right, so let's try another one here. Molecular iodine dissociates with a first order rate constant 0.271. What's the half-life of this equation or this reaction? So once again here, first order. So we are looking for half-life. So we do want to use obviously our half-life equation, natural log of 2 divided by k. In this case, obviously they gave us the rate constant where we could also, if we were not told, figure out that it was first order here. Gonna get us a 0.271er. And we got something like 2.56 seconds, I think. Again, the seconds come to the top, obviously, when you divide it. Is this a very fast half-life or slow? Very fast. Every like 2 seconds, like half of it's gone. Yeah, so makes for a quick day, I suppose, if you're using it or whatever that might be there. Any questions on all that? Yeah. Okay. All right. So in addition to first order reactions, there are some other common reactions that we come across that you also do need to know. The next one that we're going to talk about are second order reactions. And second order reactions do have a little bit of different sort of equations that we want to use for these guys. And there's really, again, you know, a couple ways or common ways that you could get to a second order reaction overall. Obviously, you could have one reactant that is just second order. You could also have 2 reactants where they're each first order, right? Will get you to a second order reaction overall. If we write our rate law for a second order reaction in this example here, it will look something like this. The rate is equal to K times the concentration of A squared. Solving for the rate constant, what we see are, again, the typical units associated with a second order equation or reaction, which we saw earlier on in some of the calculations that we did. This is 1 over molar seconds, but just like first order, it really doesn't have to be seconds. It's some unit of time. So you could have 1 over molar minutes, 1 over molar hours, something like that. But wherever you get 1 over molar times some unit of time will tell you that it is a second order reaction. And once again, this also could be written like that, right? As well. And again, that does obviously vary from the first order that we just saw, which has 1 over seconds as the typical units that we associate with it. It also has a integrated rate law, which is this guy right here. This is 1 over the concentration is equal to 1 over the initial concentration plus a KT. And it has a half-life equation, which is also different than what we see with a first order. The half-life for a second order reaction is 1 over K times the initial concentration. So unlike the first order reaction, which is frankly independent of the initial concentration, the second order reaction's half-life is dependent on the concentration of the initial concentration of the reactant. It's on the bottom, right? Which means larger concentration, I end up with a smaller or larger number when I just mathematically divide it. So if the initial concentration is large here, my half-life will be small. Yeah. So the larger the initial concentration, the smaller the half-life. It makes sense if you just logically think about it, right? If you have a large concentration, that means there's more of them there to start reacting, right? So it's going to react, perhaps going to react a little faster. So we do see that. And obviously, if we have a smaller concentration there to begin with, we would see the half-life obviously go up. So again, the initial concentration here is going to have an effect on the half-life of this particular type of reaction. Again, looking at our linear relationship, we could take that integrated rate law and rewrite it. That 1 over A is equal to KT plus 1 over A naught. And once again, this would be written in the form of a straight line, or this would be y is equal to mx plus b. So once again, what we would graph for a second order graph to give us a linear relationship would be on the y-axis here, 1 over the concentration. On the x will be our time. And once again here, this should give us a linear relationship and a best fit line where the slope in this case is going to equal the rate constant. The slope of this line is going to be positive, right? So that's why in this case, the slope of the line equals the rate constant, giving us our positive value for our rate constant. Any questions on that? Yeah. It actually is, truthfully, I'm not sure what the subscript is, but I think it's, I think it's just like a little typo kind of thing. Yeah. So it actually should be the final concentrations, but it is. So they might have wrote F or something like that, or that was supposed to be a small F or something like that, but it's really your final concentration. Yep. Other questions? Got it. So much like our first order, there's several things that you should definitely know for second order. Once again, we're talking the appropriate units that are associated with the second order. Our rate law here that helps us understand concentration versus time, the half-life equation, and once again, the graph here that is associated with a second order graph. As you can see here, what is graphed here is very different than what is graphed on the first order. And as we'll talk about, you can use graphing to help you determine, what order the reaction will be. Also known as the second kinetics experiment, where you make like 400 graphs and determine things experimentally or graphically what the orders of the reaction are. Any questions on that there? Okay. The next and really the last sort of common order of a reaction that we're going to talk about really in this class and in most classes that you talk about are zero order reactions. And once again, zero order reactions, for the most part, is usually one reactant, where that obviously is to the zero order. And once again, if we did write our rate law for that, the rate would actually equal K, because A to the 0 is 1. So the rate equals the rate constant here, which means it's really easy to know these units. The typical units that we see for a zero order reaction are actually the same units that we see for rate, which is molarity over seconds. And again, once again, the time can be any time, but seconds is the most common one that you see there. We also have a concentration versus time version of our zero order, and it looks just like our first order, except no natural log action happening there. So it's in our concentration. Final concentration is equal to our initial concentration minus the rate constant times time. And once again here, we see a different half-life equation, which is the initial concentration divided by 2 times the rate constant. So much like the second order reaction, the zero order reaction half-life is also dependent on the initial concentration. And in this particular case, if I have a large initial concentration, will my half-life be longer or shorter? What do you think? So let's just say randomly my initial concentration was 50, right? 50 divided by 2 is how much? 25. Let's say instead of 50 for my initial concentration was 20. 20 divided by 2 is? The one that has the faster half-life is? A lower concentration, right? 10 seconds versus like whatever the other one was, 25. Yeah. Just simple math here. Yes. So it's a good way to think about things. Just simple numbers, right? Is the way to think about it, right? So again, in this case, the smaller concentration, right, is going to obviously yield you a shorter half-life, right? And it's going to occur faster. Larger concentration will obviously, in this case, yield you a little longer of a half-life, more time for those guys to sort of react. So again, there is some differences, and depending on the concentrations that we see, you may see the half-life being longer or shorter. Once again, we can look for our linear relationship here by rearranging this equation, very much like we did the others. This will be A is equal to minus KT plus the natural log of A naught. And once again, that would yield you your Y is equal to MX plus B. Once again, this tells us what we should put on our graph. That is our final concentration. So I'm just gonna go with that, maybe like an F or something that we want to do that. Actually, what it really is, if I look at it really closely, is actually the concentration at the time is basically what that little guy is. So it's really your final concentration, but I think that's what they kind of scribbled down there. On the X would be our time. And once again, this should give us a linear relationship if it is zero order. And when we look at this line, we see that the slope is negative. So in this case, the slope will equal negative the rate constant. And again, that will get us back to a positive value for the rate constant when we do this. So once again here, much like the other ones, the important info, we got our units, our specific one for zero, our half-life here, and obviously our concentration of our graph there that we should know. Any questions on that there? All right, so let's take a look at one here, I think. So this reaction is second order in Q. If the initial concentration of Q is 0.01 molar, after about 500 seconds, the concentration goes to 0.001. What is the rate constant in this case? So take a minute to see what you come up with. Okay, let's, before we do, let me think about one thing there before we move too far away from zero order. Speaking of the graph in terms of zero order here, we did see this graph earlier, if you remember. So we saw this really same thing sort of graphed, and we saw what was graphed was exactly the same thing, which was concentration versus time. And in a first order, though, it did not give us a linear relationship. It gave us that one that was just kind of decreasing with time. So again, you might see this sort of same graph two different ways. If you see it like the top way here, where it's really not a linear relationship, is probably going to be a first order reaction that we're dealing with. If you see those exact same things graphed here, like we see here, and it does yield you that linear relationship, then we're obviously talking about zero order. So those two graphs are sometimes obviously both actually used. So you should keep that in mind as well. Any questions on that there? Okay, so coming to our problem here, it is second order. So clearly we want to make sure we use our second order formula to do so. And that should be something 1 over A is equal to 1 over A naught plus a KT. In this case, let's see here, we got some initial concentration, which is 0.01 molar. We have time, which is essentially 500 seconds, I believe. We got our final concentration here of 0.0010. That's a lot of ones and zeros. All right, so we have everything here except for obviously the rate constant we're looking for. So plugging this in would give us 1 over 0.001 is equal to 1 over 0.01 plus K, which is what we're looking for, and our 500 seconds, right? So once again, here we're going to, personally, I'm going to take 1 divided by 0.001. And then I'm going to subtract this to the other side. And I'm going to subtract 1 divided by 0.01. That gives me 900 is equal to K times 500 seconds. I'm obviously going to divide my 500 seconds over. And in this case here, that's going to give me 1.8 units would be molarity up on top, and seconds as molarity is basically over here. Yes. Any questions on that there? Yeah. I'm sorry. The molarity should be on the bottom. There. Sorry about that. So it should be 1 over molar seconds would be the right way to do it. Yes. You do. Yeah, so they will not be provided for you. No. Yeah, yeah. Yeah. So again, all those things that I highlighted, you need to know. Yeah. So including obviously the graphs and stuff like that. Yeah. Other questions? So typically speaking, as we talked about, I think at the beginning, formulas and stuff like that will not be provided for you. Any type of constant values or conversions would be provided. Anything that would come from a table obviously would be provided for you and stuff like that. Other questions on that there? So I guess properly, this would be 1 over molar. So okay, so here's sort of a summary that might answer the question that was just asked. Yeah, you need to know basically this column and this column. Yeah. So we do want to always make sure that we are using obviously the appropriate formulas for the appropriate equations. And this is obviously a mathematical approach that you can figure out the orders of a reaction by doing so. Graphically as well is a way that you can determine the orders of reaction. And as I mentioned, when we get to the, I think it's called the kinetics activity, that's essentially what you're going to do. You're basically going to do all 3 of these graphs for every experiment that there is. And you're going to be doing some linear regression, trend line, get your equation, your R squared value. And your R squared value, right, is your linear coefficient. And the one closest to 1 is the most linear, right? So you could do all these graphs and you'll be able to determine which one has an R squared value closest to 1 or the closest to 1. And that would tell you what the order of the reaction is graphically. So it's why it's important. You also do need to know the graphs associated with each of these. So once again, if you got a linear relationship of concentration versus time, it's going to be 0 order. If you got a linear relationship of natural log of A versus time, it will be first order. And if you have 1 over A versus time, and you get that linear graph, you will have a second order equation overall. So kinetics is all about graphs and tables and things like this. So, you'll see a lot of them. Any questions on that? So the next thing we're going to talk about is actually energy and temperature and its relationship to the rate of a reaction. So the first thing we want to talk about is, in terms of energy, the differences between the 2 types of energy reactions that sort of occur. One is exothermic, and exothermic means that heat in energy is released. Endothermic, on the other hand, means that heat and energy is absorbed, right? Or energy is absorbed. And what we are looking at are what are referred to as energy diagrams. And you might be familiar with them from your energy talk in Chem 50, perhaps. We've seen something that looks like this before. Yes. Okay, good. So on the left is a typical exothermic diagram. We have our reactants and our products. The reason we know that this is an exothermic diagram is why? The reactants are higher in energy than the products, which means the only way to get down to the products is energy has to be released, hence the exothermic part of it. Yeah. So in this case, because the reactants are higher in energy than the products, energy is given off. And it would be an exothermic reaction. That is also why we know the guy on the right there is an endothermic reaction. The reactants are lower in energy than the products. which means in order to get up to the product's energy, we got to put a little energy in, yeah, to sort of do that move. What happens when a reaction takes place is pretty much two things kind of need to occur, sometimes referred to as collision theory, which means, frankly, they need to hit each other, right? So there needs to be some type of collision that occurs between molecules. Those collisions actually need to be in the right location. They need to be like on like the active side, if you will, in the right spot when they collide. They also need to collide with enough energy basically for that reaction to occur. And there is a minimum amount of energy that's required for a reaction to occur, and that is what is known as the activation energy. So the activation energy is really the hill that the reactant's got to climb to get to the other side to make products. So not all collisions, when two things come together, results in products being formed. They got to hit each other in the right location. They also have to have the sufficient amount of energy to get that reaction basically to take place. When we have a chemical reaction, right, the only things that really happen is what happens during a chemical reaction. How do the reactants go from the reactants to the products? What ends up happening to the reactants? You just walk over to the product side and go, I'm here. No, no. All the bonds, right, that the reactants have, they all have to break, right? And then they have to reassemble on the other side and make all those bonds on the product side. Perhaps you did some calculations with bond energy. Yeah, bond enthalpy. I broke like 3 double bonds. It costs this much energy to do so. Anyone? Yes? They teach Chem 50 here, right? So you used to do that in like the energy chapter, maybe actually the bonding chapter, I think is a lot of times where that ends up being. But maybe you remember it. If not, there's a certain amount of energy required to break, for example, a carbon-carbon single bond, or a carbon-carbon double bond, or a carbon-carbon triple bond, or there's a certain amount of energy to make those bonds, right? By the way, which bond is the strongest, single or triple? Which one's the strongest? A triple bond is stronger than a single bond, right? And triple bond stronger than double bond. All right, so back to this class here. So what really is happening when a chemical reaction occurs is all the reactions are really just breaking apart, right? They're breaking all the bonds, but they also then has to sort of make all those new bonds. And that's essentially what's happening as this reaction is progressing. As our reactants, for example, here on this side, start moving themselves up this hill, they're really starting to break the bonds that they have, the reactants, and they're actually starting to make some new bonds. So as you sort of progress up here, we're breaking some bonds. We're making some bonds till they get to the very, very top there. And at the very, very top of the hill, in terms of energy, is what is sometimes referred to as the transition state. And what we have up there at the very top of the transition state is what is sometimes referred to as the transition state complex, or sometimes referred to as the activated complex. So let's talk a little bit about energy when things are in high states of energy. Is that a stable situation or not really a stable situation? Not really stable, right? Things don't really want to be in high energy. Ultimately, the goal of everything that happens really in chemistry is for things to get to like a nice lower state of energy, right? The most stable way that they can. So when we have this transition state complex, which is frankly at the peak of energy you could go in this process, what it exactly is something that has kind of partially made bonds and some partially broken bonds. It's like an intermediate. It's sort of changing from reactants and starting to break all those bonds, but starting to make some of those new bonds as they come down to sort of the product side. Because it's really the peak of energy up there, usually transition state complexes are really hard to isolate in a reaction because frankly, they don't hang around a very long time because they are very high in energy. And what typically happens is relatively quickly, we will see sort of this guy drop down to the other side and really make the products at that particular point. And we see the kind of the same idea here. We see the climb of the hill here as we're breaking bonds, making new bonds. We peak out over there at the transition state, and once again, going to kind of drop down relatively quickly to the other side. The actual activation energy is the energy difference, right, between where the reactants are and the peak of the hill, right? So just looking at those two diagrams, which one would perhaps move slower in terms of the rate of the reaction? The one on the right, right? It has a much bigger hill to climb. What does that mean? It means that it perhaps needs a little energy, which is why it's endothermic, right? To kind of help everybody up and over the hill. So the activation energy, or that hill that the reactants have to climb, typically has a major effect on the rate of the reaction, right? Just like us, if we had to walk up a big giant hill, it's going to maybe take us a long time to get up and over to the other side, as opposed to if we just had to go up a speed bump, right? To the other side of the speed bump, not a very big hill. We could get to the other side really quickly. In that example as well, there's probably a lot more people that could get themselves up and over the other side of the speed bump on the road, right? Then if you pointed to the giant mountain and say, I'll meet you on the other side, there's not a lot of people who's going to probably make it up and over. There will be some, right, that will have enough energy to do that. And it's the same idea with our reactants. There's a certain amount of reactants that have that minimum amount of energy to get up and over the other side. And there's some that can't do that, right? And all that affects how fast or slow a reaction takes place. Any questions on that there? So why would temperature typically increase the reaction rate? Right. So for example, if you increase the temperature, what you're essentially doing is throwing more energy in there, right? And now more reactants that maybe normally wouldn't have enough energy, right, to get to the other side will now find themselves, hey, I feel a little, I had a good breakfast this morning. I could get up and over to the other side. I have a lot more energy to do that. So by increasing the temperature, what we're doing is providing a lot of energy, which gives a greater proportion of reactant molecules enough energy to hop over to the other side. The result of that is we see the reaction should occur a lot faster. Vice versa, if we decide to throw everything on ice, that is essentially doing what? If we lower the temperature, it's essentially removing energy, right? So now in a normal situation, we have this many guys that could kind of get up and over to the other side. Now, when we lower it, these guys lose some energy, right? So there's a smaller proportion of molecules that have sufficient amount of energy to get to the other side when we lower the temperature. Any questions on that there? So the effect of temperature on the rate of reaction is what is known as the Uranus equation. And this is one version of it. We're going to see a more applicable version in a second here. But that is the rate constant times A. A is the frequency factor. A is basically the proportion of molecules that have enough energy to get to the other side, basically. And then the rest of the stuff is our normal things here. E of A is our activation energy. R is the gas constant, but it is the one that involves energy. So it is not the one that you use in the gas law. It is this one here, the 8.314 joules per Kelvin per mole. And T is temperature, and much like most things in chemistry, if it's temperature, it should be in Kelvin, right? So once again, right, that's a 273, right, plus Celsius gets you the Kelvin. So if we sort of take this formula here, and we can sort of integrate it in just a second, but we sort of talked about this here, but we'll go over the slides here. The activation energy, like I said, is really that hill that the reactants has to climb to get to the other side. That guy on top, again, is sometimes called an activated complex or a transition state complex. And it really does consist of something with sort of partially made bonds and partially broken bonds, which also leads to why it's so high in energy and also very unstable. So things with partial bonds not going to be as stable as obviously things with full bonds, if you will. And here's just an example of sort of the reaction here. If this rearrangement happens as it progresses, it's starting to break some of these bonds. This molecule here to rearrange. When it gets to the top, it's sort of in a transition state. And then we're going to sort of drop back down to the end here. And we have our activated complex that gets down to our final guy. So taking this equation that we just saw, a really more, I guess, useful version of it is actually this equation here. This is really more a graphical version of this equation, the Uranus equation. This is the natural log of K is equal to minus E of A over R times 1 over the temperature plus the natural log of A. This is actually written in the form of a straight line. This is y is equal to mx plus b. On a linear relationship, which is what this equation is used for, we would typically plot on the y the natural log of k. On the x would actually go 1 over the temperature in Kelvin. And this would give us a linear plot, which is usually a negative type of slope happening there, where you can graphically make this plot, and from the slope of the line, you can figure out that the slope is equal to minus E of A over R. R is a constant. So basically, if you take the slope and you times it by R, that will give you the value of the activation energy for that guy. A couple of things that you want to watch out for here, as we'll talk about. That line that I drew there will have a negative slope, yes. And the negative there will turn the activation energy into a positive number. And when I do that, and I take the E of A is equal to minus the slope times R, what units do I end up with in terms of energy? R is 8.314 joules per Kelvin per mole. These end up in joules. Typically, activation energy is given in kilojoules, but when you do this calculation, you actually do end up in joules. So if you want kilojoules, right, there's 1,000 joules in a kilojoule. You have to do that conversion, and activation energy should be positive, as we saw from our pictures. Here, actually, we'll go here. As we saw here, right, this is the activation energy. It is positive in both cases, so it should always be a positive number. By the way, looking at this graph here, the difference between the reactants, right, energy, and the products is your delta H of the reaction, right? So that's the overall enthalpy of the reaction by taking the difference between those two. Delta H. So to finish up, just look at that last graph here for today. We will look more at this equation and stuff in a bit. But this is just actually this guy being graphed. And that's the rate constant versus temperature. And what we see here to finish up on is what we just talked about. When we have a smaller temperature or lower temperature, the rate constant is smaller, which would imply that the reaction is going to occur slower. When we sort of have a much higher temperature, we see a much higher rate constant, which would occur, meaning that the reaction would occur a lot faster. Any questions on any of that there? All right, we will lay it up there for today's lecture.